Have you ever seen those old analog ammeters in school labs with a needle that twitches ever so slightly when current flows? That tiny twitch, that's the magic of a moving coil galvanometer. Hello students, today we are diving into a fascinating instrument that lets us detect and measure even the tiniest electric currents, the moving coil galvanometer. At its core, the galvanometer is all about converting electrical energy into mechanical rotation. How? Well, whenever a coil carrying current is placed in a magnetic field, it experiences a torque, a twisting force, and that's the key idea here. This principle makes the galvanometer a sensitive detector of electric current, especially useful when currents are too small for an ordinary ammeter to pick up. Picture this, a small current passes through a coil inside a magnetic field and boom, the coil rotates slightly. That movement is then shown on a scale using a pointer and we can now read the current. Let's now take a closer look inside the galvanometer because its construction is cleverly designed to maximize sensitivity and accuracy. First, there's a rectangular coil made of fine insulated copper wire wound tightly and mounted on a lightweight frame. This coil is either suspended or pivoted, so it's free to rotate when a force acts on it. Now, this coil is placed between the poles of a horseshoe-shaped magnet, which creates a radial magnetic field. And to ensure that field is truly radial and uniform, there's a soft iron cylinder placed inside the coil. Why is that important? Because in a radial field, the angle between the coil and magnetic field remains 90 degrees, maximizing the torque. Then there's the spring, not just any spring, but a special one that provides a restoring torque, pulling the coil back to its original position. Interestingly, this spring also acts as a path for current to enter and leave the coil. Finally, the pointer and calibrated scale convert the coil's rotation into a readable value, giving us a direct way to measure current. Now let's get to the physics that drives the galvanometer's working, torque. The principle is simple but powerful. A current-carrying coil in a magnetic field experiences a torque. The expression for that torque is tau equals NBIA sine theta, where tau is torque, N is the number of turns in the coil, B is the magnetic field strength, I is the current, A is the area of the coil, and theta is the angle between the plane of the coil and magnetic field. But wait, in our case, thanks to the radial magnetic field, theta equals 90 degrees, so sine theta becomes 1. That makes the torque simply tau equals NBIA. Now the coil is also under the influence of a restoring torque from the spring, which is K times theta, where K is the spring's torsional constant. At equilibrium, these two torques balance, NBIA equals K theta. Solving for theta, we get theta equals NBA divided by K times I. So what does this mean? The deflection angle is directly proportional to the current, a beautifully linear relationship. Here's where precision really matters. Let's talk about sensitivity. The current sensitivity tells us how much the coil deflects for a given current. Mathematically, it's theta divided by I equals NBA by K. So, to increase sensitivity, we can use a coil with more turns, a stronger magnetic field, or a larger area, all of which make the device more responsive to small currents. There's also voltage sensitivity, which includes the effect of resistance. It's given by theta by I divided by R, where R is the resistance. And then comes an important parameter called the figure of merit, symbolized by capital K. It's the current needed for unit deflection. K equals I by theta equals K divided by NBA. So in a well-designed galvanometer, sensitivity is everything. It helps scientists detect extremely weak currents in experiments, like measuring the tiny current in a photoelectric cell. Even such a beautiful instrument isn't without its flaws. First, galvanometers are fragile. applying a large current can damage the coil or spring. That's why they're not used for heavy-duty measurements. They're also sensitive to mechanical vibrations, and changes in temperature can alter the spring's properties. To overcome these, sometimes light beam pointers are used instead of physical ones, reducing the inertia and improving accuracy. But here's the cool part: we can convert a galvanometer into an ammeter or a voltmeter. To make an ammeter, we connect a low-resistance shunt in parallel, so the galvanometer handles only a small fraction of the current. To make a voltmeter, we connect a high resistance in series, allowing it to measure potential differences without drawing much current. This flexibility makes the galvanometer a true multifunctional instrument in electrical measurement. Let's solidify our understanding with a practical example. Imagine we have a galvanometer with 50 turns, a coil area of 2 square centimeters, a magnetic field of 0.1 Tesla, and a spring constant of 2 × 10 to the power of -6 Newton meter per radian. We are asked, what current is required to produce a deflection of 0.05 radians? We start with the torque equilibrium condition, N times B times I times A equals K times theta. Now solving for current I equals K times theta divided by N times B times A. Let's substitute the values. K is 2 × 10 to the power -6. Theta is 0.05. N is 50. B is 0.1. And A is 2 × 10 to the power -4 after converting from square centimeters to square meters. So, the expression becomes I equals open bracket 2 × 10 to the power -6 multiplied by 0.05 close bracket divided by open bracket 50 multiplied by 0.1 multiplied by 2 × 10 to the power -4 close bracket. Carrying out the calculation, we get I equals 0.1 milliampere. That means just a tiny current of 1/10 of a milliampere is enough to create a visible deflection in the galvanometer. That's how incredibly sensitive these instruments are. So to wrap it up, the moving coil galvanometer is a marvel of electromagnetic precision. We learned that it detects small currents using torque on a coil placed in a magnetic field, and that its design, with a radial field and soft iron core, ensures accurate, linear response. The deflection is directly proportional to current, governed by the equation theta equals NBA by K times I. Its sensitivity can be tuned, and with a little modification, it becomes a versatile ammeter or voltmeter. This humble instrument may seem old school, but it's a cornerstone of electrical measurement, still respected in labs and experiments across the world. I hope you now appreciate how such instruments bring abstract laws of physics into measurable reality. Until next time, keep questioning, keep learning. See you in the next session with another fascinating concept of physics.